Hello, everybody. Thank you for joining us this Tuesday for the latest installment in our Fall Colloquium series. It is my pleasure to introduce Professor Dong Lai, who's a Benson J. and Mary Ellen Simons Professor at Cornell University. His research interests span the dynamics of planetary systems, the nature of compact objects, and a wide range of astrophysical fluid dynamical problems. His prominent contributions in these areas has been recognized this year with the award of the 2024 Brouwer Prize, which also acknowledges his boundless enthusiasm for mentorship. Having been a visitor to the Institute over the years, it is fantastic to have him visit us again, where he'll be telling us all about the dynamical formation of merging compact binaries. So please join me in welcoming Dong to the stage.
All right. Thank you very much, Colin, for this nice but overly generous introduction. So I'm going to talk about indeed dynamical formation of black hole, LIGO black hole binaries. I'm going to go through some general slides very quickly so that we are all on the same page, right? Okay, hold on. I should do this one. Not moving. No.
If you just put it on the screen, begin with.
Should I? Okay, so now it should work now. Okay, good. So LIGO has now detected 90 compact merging binaries. Most of them are black holes. More are coming in the coming years, all right? And just a reminder, when you detect, like when LIGO detect merging black hole, merging binary, you get three numbers measured or constrained: the masses of individual black holes, and this chi effective, which is the spin parameter of the binary, which is basically the chi1, chi2 are the individual spin parameter of the black holes. So this mass weighted projected along the orbital angular axis. So this is a quantity that can be also constrained, okay? So these are three measurables. What? I touched something. I should not. Okay, so what can you do with these gravitational waves, right? Test gravity. Of course, many people are interested in doing this thing. So far, what I heard is that GR works very well so far, but in the coming years, there will be more tests. You can study dense nuclear matter, right? When they think when the two neutrons merge, there all kinds of things can happen. There are really two kinds of things you can do, right? In spiral phase, during the spiral phase, you can have, the tidal deformation of the two neutron stars getting closer. They're no longer point masses, tidally deformed, and that can change the waveform a little bit, a phase shift, phase evolution of the gravitational wave that can be measured, can be constrained. And this effect is well understood. There are tons of paper on this subject over the last few years. And another aspect I always like to talk about is resonance tides, where basically what you have is that neutron star has internal oscillation modes. That modes could have low frequency, for example, 100 Hertz. So you have this harmonic oscillator, the companion, moving around you, and then that companion serves as an external driver, right? And that the driver has the frequencies gradually, the forcing frequency gradually going up. At some point, that forcing frequency will match the the harmonic oscillator frequency, 100 Hertz. In that case, the orbital energy will be pumped into the internal mode. So if you plot the orbital energy, the function of time, it's gradually decaying because of gravitational radiation, and then suddenly go down, and then right there, the kink, and that delta E, that the change in energy, right, in orbital energy, that can give rise to, if the effect is big enough, that can give rise to a phase shift of different kind, right? That phase shift can happen even when the two neutron stars are far away from each other, right? And this could happen. So, this could still, I'm still hopeful this can happen. Really depends the size of that phase shift. Really depends on the equational state of neutron star. In particular, the radius of neutron star. 10 kilometer and 12 kilometer make a big difference. Okay, so that is okay. So far, this has not been measured, has not been constrained, but I'm hopeful there could be, depending on whether nature give us this bigger neutron star, right? And of course, when you have merger, eventually when you have these two nuclear matter collide with each other, you can have all kinds of signatures, right? The remnant neutron star could be different kinds of hypermassive or supermassive neutron stars, or could become black hole, right? And this, hopefully, in the coming years, there'll be signature of these kind of things, right? Now, when we do science, we always hope there's some surprising things, right? So this being Princeton, I think we should keep in mind that there's a possibility. We hope there are some surprising things, right? Maybe this two neutron star could be a quark star, right? And I know some old timers know that the late Bogdan-Paczynski was very interested in quark stars. I think before in the 1990s, he was very interested in these kind of things. So I think we should keep an open mind. There's a possibility that it could be quark stars. So let me say a few words about this, right? And so again, there was a famous conjecture some years ago by Witten that strange quark matter could be the most stable object in the universe. So there's a possibility that you could have this bare, strange quark star, right? And with maybe it's a little bit of atmosphere on top, right? And so far, when I talk to the nuclear physicists, these hypotheses have not been confirmed or ruled out. So let's see what's going to happen, right? So here's an interesting physics problem that apparently have not been done properly. I found recently. Basically, if you have let's say, imagine you have a quark star and being tidally disrupted by a black hole, right? This quark matter initially is confined quark matter. It's decompressed, going to low density. So here's the question: how does it become? What's it going to become? When you decompress this chunk of quark matter? What's going to happen to the matter, right? So there are actually two possibilities, I think, right? One possibility is that you decompress, this thing will just phase transition into normal nuclear matter, NPE gas, right? But another possibility is that you become a gas of quark nugget, where each nugget is big, it's a big thing. It's just like a big boulder, you break it up. It does not break up into individual atoms, break up into sands, that kind of thing. So this can be studied, right? And the answer, of course, as you can imagine, is still uncertain. Depends on this delta E, which is, in a way, the binding energy of the quark matter relative to nuclear matter, which is uncertain. There's still, range. It depends on temperature of this decompressed matter, right? So if you, for example, you can see, 20 MeV, 60 MeV, the temperature 20 MeV, so you can have a situation either depending on the precise condition, you can get different possibilities, right? Now, why do you care? Well, I think you can imagine if you decompress this quark matter into this kind of nugget gas, then you can actually compute these. It's not going to compute the neutron, the proton fraction. It's not going to be neutron rich, right? This will not give rise to any kilonova or nuclear synthesis. So this is actually qualitatively very different from the normal things, okay? So this is just a possibility, right? So I personally believe most likely these are neutron stars, but I think we should keep in mind that there's possibility, right? And all right, yes?
So the fact that we did observe some interesting electromagnetic radiation,
one, yes, but they are as you know, there's the latest, I'm speculating now, the 04, they found quite a few neutrons of black hole, they had no kilonova, so. Yeah.
I was curious, is it possible that in some parts of mass space, you have the quark star and other parts of mass space?
We don't know. I think this is just, nobody has done this kind of calculation, apparently. I just really want to bring this up.
Those calculations presumably depend on the detailed equations. It's a QCD calculation.
It's actually not. It's actually the bulk matter is a QCD, the bulk part. But when you decompress it, it's really phase equilibrium between the sort of the space in between. There's a lot of space between the quark, right, quark matter and then quark nugget, and then it's phase. So there's two phases. I don't want to go into detail, but this is basically the equilibrium stage when everything is in equilibrium. There's the sort of the beta equilibrium, equilibrium between the quark inside the nugget and the stuff outside. You do phase equilibrium, and then there is also the non-equilibrium calculation we have done. I mean, this is very speculative, of course. I mean, just I bring this up just to say, we want to keep an open mind. And it would be wonderful we have these things, right? This quark star, right? Okay, so you can study nuclear synthesis, electromagnetic counterpart. We have this famous event, of course, we all know, right? And then finally, of course, that's we all care about where do these merging black hole binary come from? What do we do with these things, right? So in the coming years, there'll be thousands of merging black hole detected, and what are we going to do? What are we going to learn with this? So this has to do with astrophysics of binary black hole formation. So that's what I want to talk about in the remainder of the talk. Okay. And then, of course, there is this so-called final AU problem. If you have two black hole orbiting around each other, it's radiating gravitational waves, but if the separation is too large, the merger time will be larger than Hubble time. They're not going to merge, right? So therefore, if you want to have these two black holes to merge within Hubble time, let's say 30 plus 30 black hole binary, if you want them to merge within Hubble time, the separation should be less than AU also, right? So this is right. There are a lot of binary black holes, but a lot of time they may be far away from each other, right? You want to, how do you bring them together, right? So that is the question. And so there are now, of course, many possible formation channels for these merging black hole binaries. And the standard model, when we do science, of course, the still we should be conservative, right? I think the standard model still is isolated binary evolution. And then there are several different flavors of dynamical formation channels involving dense star clusters, involving triples and multiples, involving AG and disks, all right? Now, before I go into these different channels, let me just quickly remind us what are the possible ways we can tell the difference, right? We potentially constrain these different channels, right? The rates, as you can imagine, can be very uncertain, and each of these channels can be very uncertain. Sometimes the physics may be very clean, but the environment, the astronomy is very uncertain. And I'm not going to say too much about the math, the rates. And the mass ratio of the black hole binaries are so very interesting. And here is the sort of current situation for the primary mass distribution of the merging black hole binary. There are a lot of features, right? And this solar mass bump may be natural if you think about the formation, supernova formation of neutron star black holes. The 30 solar mass bump apparently is real. Everybody tell me this is real, and I don't know where they come from. Maybe Adam Burrows knows, and it's not clear where they come from. Okay, this seems to be real, and the people are now jumping ahead. You assuming this is real, and then do cosmology with it, right? But we can do these kind of things. Okay, so that's a puzzle, and the residual eccentricity. So the gravitational wave make the orbit decays, but also circularize the orbit. So in most situations, when the binary enter the LIGO band, they are very close to each other. The orbit will be circular, but there will be situations in the dynamical channel where the binary are formed sort of so eccentric. So by the time they enter the LIGO band, they still have some residual eccentricity. So this residual eccentricity is very interesting, right? And so that's another thing can look out for. And then the spin orbit misalignment, right? The angle between the spin of the individual black hole and the orbital angle on the axis of the binary. That angle it's also interesting thing. The reason is that this chi effective, as I told you, can be constrained or measured, right? And this chi effective depends not only on the magnitude of chi1, chi2, but also on the angle between the spin and orbit. So this is also can be constrained, right? And so that's why it's relevant. And finally, the possibility of electromagnetic counterpart, even in the black hole case, black hole merger. So if you have, normally if the merger happening in vacuum, we don't expect any counterpart. But if you have situation where the merger is happening in some gaseous environment, you could imagine some very faint counterpart, right? And that's another thing that one can potentially look out for. Okay, so that's the sort of a possible thing to keep in mind. Now with that, let's talk about the standard models, isolated binary evolution. These have been worked on for many decades, right? And it's most likely will happen because we see close binaries, create actually low matrix binary, all the kind of things, CVs, right? And the key, but the physics uncertainty is still there. The common envelope exactly is where you have this black hole enter in the envelope of the other star, and then the orbit shrinks, and that's crucial for making the binary small. And that physics still uncertain, right? And some of you may know this Gaia black hole 1, 2, 3, the latest, and that actually shows that our understanding of the existence of the orbital property of this three black hole with a normal star, and actually pretty strange, a bit strange, and it shows that our understanding of common envelope phase is actually quite incomplete. There's some problem with these things, okay, to explain this three Gaia black holes. Regardless of this uncertainty, if you believe this works, then you typically will produce circular orbit, right? Because you have all this gaseous damping, gas effect, the damping eccentricity. And when you enter the LIGO band, most likely the orbit will be circular, and then the most likely will be aligned, more or less aligned, okay? So that's the isolated binary evolution. Then we have several flavors of dynamical formation channels, right? The first one that you heard a lot about is the dense star clusters, where you have all kinds of interaction between the binary system and stars. The most important one being binary single scattering, where you have a binary black hole, they are separated from each other, but they cannot merge by themselves, and then they have encounter with another single object, right? In that process, they have this chaotic three-body interactions, and then one of them will be ejected, taking away energy and angular momentum, leaving behind a more bound, more eccentric binary, and that binary can merge, right? So lots of people have been written on this subject, and the physics is very clean, right? And the uncertainty is mainly the astronomical uncertainty, environmental uncertainties, right? We don't know how many black holes are there you can keep in the globular cluster. So maybe you need a nuclear star cluster and so on, right? And most calculation of these kind of channels, this kind of dense star cluster produce a circular orbit when the system enter the LIGO band, and simply because the binary that's left behind after the three-body interactions are still very big, and then when they enter the LIGO band, they'll be circular. And then you expect random spin orbit orientations, right? In this case, because you have this, three-body, chaotic motion that changes the orbital orientation, right? So that's the general expectation. Okay, and then a second class of possibilities also involves three bodies or four bodies. I call that tertiary-induced merger, right? In this case, you have a binary here, right? They are orbiting around each other. They don't merge by themselves because the separation is too big. And instead, you have a third body, which is far away, or some other body far away. They don't come in close to the binary in the region. They don't have strong chaotic, three-body interactions. The third body is far away and then moving around, right? And then with the help of time, over time, this third body under some conditions can make the inner orbit, change the shape of the inner orbit, making the orbit very eccentric. And then this inner binary can merge, right? When they get very close, sufficiently close to each other at pericenter, they can have radiated gravitational waves and therefore can merge, right? And these kind of mechanism can happen both in the galactic field, where you have stellar triples. For massive stars, triples are very common, actually, 50% massive stars. These are progenitor of black holes. Triples are very common, right? So this is not as like, so you have a galactic field, you have binary, and then you have a third star, right? Or could be happening in nuclear star clusters, where you have a binary moving around the supermassive black hole, in which case the tertiary is actually a supermassive black hole, right? Exerting a torque, exerting a force on the binary that you want to merge, right? The key physics, one of the key physics is this Lidov-Kozai effect that I'm sure many people heard about, but just make sure for the student we are on the same page, right? And this is discovered or rediscovered in the 1960s when people worried about, whether the artificial satellite launched from the Earth, they will fall down due to the perturbation from the moon, right? And because this artificial satellite are very close to the Earth's surface, so if you become eccentric, you will crash, right? So there was a very delightful paper by Scott and another person. I think the title is called "Why the Moon Does Not Fall." Why the satellite does not fall. It's this paper. All right. Okay, so here's what's happening, right? So basically, you have an inner binary in circular orbit, and you have an external perturber on the inclined orbit. They are far away from each other, so it's a hierarchical triple, right? And right, what happens is that if the inclination angle between the two orbits is greater than 40 degrees, then the inner orbit, the circular orbit, is unstable, cannot stay circular. If it's less than 40 degrees, circular orbit remains stable, but if it's greater than 40 degrees, the inner orbit cannot remain circular, right? It's, right, so this is somewhat surprising, and it's one of the surprises in celestial mechanics, right? And moreover, if the inclination angle is large, let's say 85 degrees, then this inner binary become very eccentric, can become very, very eccentric. In fact, it undergoes periodic excursion into high eccentricity. At the same time, the inclination angle can change, right? So in this example, you can see, right, 1 minus e initially is 1. That means the inner orbit is 0 eccentricity initially. But then because of perturbation from this external body, the 1 minus e become 10 to the minus 2, right? So the eccentricity is 0.99, right? Become very eccentric, and right, and so that's the right. So here is the example how it works, right? So here is a black hole binary, 30 plus 20 solar mass, separation 100 AU, so they can't merge by themselves, right? It's beyond the AU, right? Cannot merge, but you have a third body, which is 30 solar mass, very far away, 6,000 AU away, so very far away, and you can see, so initially the inner binary it's basically circular, right? But you can see this log time, and you can see the eccentric 1 minus e of the inner binary. Initially, is basically circular, but then undergo this excursion into high eccentricity. When it gets very close to each other, high eccentricity phase, the radiation, gravitational radiation is very efficient, and therefore you can see the semi-major axis gradually get reduced, and eventually they will merge. Okay, so that's how this mechanism works. Now, of course, we are not the first to study this. Many people actually have studied this thing over the years in different contexts. Many papers on this subject, right? And this is what we have been doing with a former student and you both here, and right. And I should say this third body, if you generalize this, so here I'm talking about binary, you have third body, but if you think more broadly, you can think about general class of this mechanism where you can imagine the third body could be a potential, galactic potential. So the galactic potential, they can, if you have put a binary here, a certain kind of potential, the potential can make the inner orbit eccentric, right? And this is how the comet, this classic paper by Hessler-Tremaine, and you can make the comet become very eccentric. They get delivered in the similar kind of idea been developed by Chris and Roman Rosikoff here. Okay, so this is not a third body, but it's effectively like a third body. Right? It's some kind of potential. Okay. All right, so I'm not going to go to the detail of all these things, but I just summarize some of the predictions of this kind of tertiary-induced merger channel, right? And okay, so this prediction is put a quotation mark. It means it's not so clean. It's not like mathematics prediction. There's some, you have to put in some distribution, that kind of things, right? And it's generic, some general prediction, so-called prediction, right? So the first, you do have some fractional system. Yes.
know much about tertiaries and massive stars out of many thousands of AU? How well constrained is that?
Not well, but people, yeah, not well. There are tertiary massive stars. The sample is small. Few dozens, I think, this guy, right? And what people usually do is just assume that whenever we know about binary, there's a semi-major axis distribution, and the tertiary has a similar kind of power law scaling, right? And so
that a few systems are known as just a limitation of the observations rather than a statement that these are intrinsically rare. Is that correct? We don't really know what the rate is, or how much.
oh, the occurrence rate of tertiary is high, actually. It's high. It's 50%, 30%. It's high. Yeah. So that's why I put this prediction. It's not really a clean prediction. It's just some general thing, right? So you do get some kind of, a fraction of the system, maybe a few percent. You can have some leftover residual eccentricity, right? Entering the LIGO band. And in this mechanism, at least in some flavor of the mechanism, you can get, general broad spin orbit misalignment angle. There's a preference peak around 90 degrees, and it's actually interesting. And in the galactic field, so I talked about, you have binary, you have a third body, it's another star, another small black hole, right? And induced by another star, everything being equal, this mechanism tend to give you unequal mass merger, everything being equal. So this might be interesting. It will give you lot of unequal mass merger. I explain in a minute. And then in the case of nuclear star cluster, where you have this, tertiary, the supermassive black hole, there are a lot of interesting novel dynamic that can happen. For example, if the binary is it's sufficiently close to the supermassive black hole, the spin of the supermassive black hole can actually affect the quasi-dynamics, can interfere, can coupled to the quasi-dynamics, right? And that can increase the rate, right? And if you couple the black hole potential and the galactic tidal potential, they can also sometimes enhance the rate, right? Enhance the rate. And then I just heard a very nice from Myla yesterday at university. There's a very nice paper about synergy between the galactic tide and stellar flyby. When you have a binary embedded in cluster, the quasi, supermassive black hole induced quasi on the binary, but you also have stars flying by that can sometimes enhance the merger fraction. Okay. Now let me just focus on this. Just spend a few minutes on this particular thing, right? And basically, in galactic field, everything being equal, you prefer unequal mass merger, right? And this can be potentially constrained by LIGO data. Okay, so we're talking about lead-off quasi effect, right? The leading order lead-off quasi effect is basically you have a binary sitting here, you have an external body, right? Far away. The leading order effect is basically the third body exerted quadruple tidal potential. It's tidal potential, L equal 2 tidal potential, right? And that's of order this, right? In that order, that's a leading order. In that order, everything is very clean. You can calculate this thing analytically, right? For example, you can predict just look at this dashed line, just focus on the dashed line. You can actually calculate the maximum eccentricity the inner binary can get as a function of the inclination between the two orbits. This curve is analytic, right? It's analytic. And you see that you reach extreme eccentricity at inclination angle of 90 degrees. But this eccentricity is not, this is not zero. It's actually finite, 1 minus E max. It's not it's a limiting eccentricity. The reason this 1 minus E max is not zero, or eccentricity is not exactly 1, is because the inner binary become very eccentric. Two black holes become very close to each other. GR effect, apsidal precession due to general relativity, detune the lead-off quasi cycle, sort of scramble up the face of the orbit. So they, usually the lead-off quasi effect is entirely Newtonian effect, but when the the two black holes get very close to each other, there's a strong apsidal precession between the inner orbit that sort of scramble up the face, so you destroy the lead-off quasi cycle. That is the origin of this limiting eccentricity that can be calculated exactly, okay? And now, if you include, so that's a leading order effect. This one, this analytical curve. Now, if you add the high order correction, just like to quadrupole expansion, include the octuple effect, right? And the octuple effect, depends on this, additional dimensions relative to the quadrupole effect, depends on A over A out, the A of the inner binary, A out the outer binary, and depends on the eccentricity of the outer binary. It also depends on mass ratio, M1 minus M2. Okay, so this strength of octuple effect depends on this dimensionless ratio, right? If you include it, you get, instead of getting this clean dashed curve, you get these dots, a lot of these dots. The reason it's all these dots is because the orbit evolution become chaotic, right? It's chaotic or quasi-chaotic, right? And so you don't have a clean thing. Nevertheless, you see that, this dotted line, you can see there is still a limiting eccentricity. That limiting eccentricity is still, given by the original one that you can calculate analytically. The only thing that the quadrupole, octuple high order correction does is to widen the window of extreme eccentricity excitation, right? So in the pure quadrupole case, you get extreme eccentricity only when you're very close to 90 degrees. But when you add an octupole, this window become larger. You get a chance to widen in the window, okay? And here's another way we finally can actually prove this. So I've been obsessed with trying to prove this thing. Why is if this strand, you add this thing, you still have the same, even though it's chaotic, you still have the limiting eccentricity. This is actually, we actually proved it recently. Anyway, so that is going back to, so there is this widening of the extreme eccentricity window. So that means that if you have strong octuple effect that tend to, if you imagine the perturber is in random orientation, then they can have a more probability, more fraction of induced merger, right? So that is why, let me skip this thing. That is why if you actually compute the merger fraction, right, everything being the same, you just look at one of the curves. If the mass ratio of the inner binary is equal to 1, right, equal mass, no octupole, then you can see the fraction is very small, 5%, few percent. Because you have to be very close to 90 degrees to induce large eccentricity to make the inner binary merge. But when you make the mass ratio different, less than 1, then you get this huge bumping up, right? It's because of this, if you increase, change the mass ratio, the octuple effect, high order effect become important, widening the merger window. Okay, so this can be understood. So therefore you have a prediction. Everything being equal, I'm being vague here, you actually prefer this particular flavor of merger, tertiary-induced merger, tend to give you an equal mass merger. Now you can ask, is it consistent with observation? Yes, Jeremy.
Jim, slightly quicker on the follow.
Yeah.
Well, this is still within secular theory, right? So,
yes.
This will drop that assumption.
Yeah. Double average, yeah, this is right. This is a particular example, right? This one is basically, I'm doing this is a particular example where 100 AU inner binary, and the tertiary, it's 3,000 AU away, and this particular thing. And it's designed such that all these points have the same quadrupole strength, but right, same quadrupole strength. All these things, you change the mass, they all have the same quadrant, but if you change the mass ratio, the octuple strength changes. So if you go to low mass ratio, and then octuple strength increases. Yeah, regarding, again, this calculation is assuming double averaging for people, you have essentially secular perturbation theory. You have inner orbit is averaged over the orbit. The outer orbit is also averaged. The reason you average that is because this kind of effect, it's taking place on very long time scale, much longer than the period of the orbits. But Jeremy, you're right. There are a lot of concern about sometimes you cannot do the double averaging. In that case, you have to be more careful. So we have done, some of the people have done that kind of thing. Okay, but that's the essential physics.
Am I right in thinking that if you include these short time scale non-secular fluctuations, everything will get boosted, but it won't depend so strongly on the mass ratio? You still have this differentiation in mass ratio.
I think you still have some mass ratio. Yeah, it has mass ratio dependence. Yeah. Okay, so does it how does it confront with observation? So here is the current LIGO data, basically, right? So here is merger rate, right? The function mass ratio, right? And so most of the merger is roughly comparable mass. Nothing, there's no peak here, right? Of course, big error bar, right? This range, this is solid line, right? And so maybe you can already say this is incompatible with observation because there's no peak here, right? But of course, one has to be careful. Maybe nature produced this binary. They already prefer equal mass. I mean, so they have to, right? But I'm bringing this up just to say, I think even we spend some time on this kind of problem. It's perfectly fine for me if this can be ruled out. I think it would be great because there's so many models these days, right? It's good to, have prediction that use of observation can rule out this thing. That would be nice, I think. So this can be potentially ruled out, but not yet at this point. Okay, so that's all I want to say about the tertiary-induced merger. I think I have 20, maybe 15 minutes. 15 minutes. Okay, so that's the second. Now let me. Okay, wow. Before I move on to the third AGN disks, right? Let me just tell you this related problem. It's a bit different. It's somewhat cute, right? So I have been talking about binary here, right? You have a third body, and the third body is gravity acting on the inner binary, making the inner binary merge, right? But now what about the opposite problem? Let's imagine you have a binary by itself is merging. Suppose you have a low mass object, a point mass, a small low mass star, something. The question is, what's going to happen? The inner binary merge, is there any imprint? Does it leave behind imprint on the orbit of the third star, right? So it's you can imagine M3 could be small mass, low mass, point mass. It's a test particle. What's happening? Is there this merging, and what happened to the orbit, right? And it's actually an interesting problem, right? So here's the example, interesting example, right? So here, look at the, okay, so here it's the black line. It's the semi-major axis of inner binary. It's decaying over time, over billions of years, gradually decay. The eccentricity of the inner binary is also gradually decay. It's gravitational radiation, shrinking the orbit and circularizing the orbit. The orange line is the orbital parameters of the test particle, outside test particle, right? M3. The semi-major axis is constant, does not change because there is secular problem. It's nothing, it's not draining energy. But look at the eccentricity. So look at the yellow here in the bottom panel. The initial orbit of test particle, it's essentially small eccentricity, essentially close to zero. But then somehow, as time goes on, the eccentricity of this thing began to grow and keep going. Okay, now what's happening? What's happening? What's happening is the following, right? The inner binary, is shrinking, but of course you have general relativity. The inner orbit is somewhat eccentric. It's undergoing apsidal precession, right? So undergoing apsidal precession, the precession rate increases as the inner orbit decays, right? As it's getting closer and closer, the precession rate goes up. The outer orbit, outer test particle is always moving around the binary. It's also undergoing apsidal precession, driven by the binary, inner binary. The inner binary is like a quadrupole, right? It's exerting potential on the thing. So the outer particle is also undergoing apsidal precession. The precession rate depends, A in square, the inner binary orbit, and depends on the outer, right? It depends on the eccentricity. So you have a situation where the inner orbit apsidal precession rate goes up. This outer one is usually go down, right? The outer one, the inner orbit becomes smaller and smaller. And of course, it's not going to be going to process more slowly. At some point, they may meet. When they meet, they get captured into resonance. Once it's captured into resonance, but another thing you notice that this precession rate of the outer particle depends also on the eccentricity. Somehow the system will want to, they locked into the resonance so that this whole thing stays together such that, the way you stay together is because you're changing the eccentricity, right? Even though this A in is increasing, but if you make the E out, the outer particle essentially goes up, then this thing can stay together. So that's what happened, it's locked into the resonance. Okay, so that's you can generate highly eccentric test particle the inner orbit decays. So you can speculate that you can do this more formally, Hamiltonian dynamics, but you can get captured. Okay, so that's just a little cute physics problem. And so remaining 15 minutes, 10 minutes, let me just talk about this final dynamical channel involving AGN disks. Right, so right, so we're talking about basically the black hole binary, small black hole binary merging inside the AGN, possibility of merging inside the AGN disks. Now, a lot of people doing AGN here, a lot of history doing AGN here, right? And it's well known in galactic center. There are a lot of OB stars. They're in the disky configuration. Also in AGN, and a lot of papers basically saying that it goes to the central region of the AGN. It's metal rich, right? That metal rich. This is actually independent of redshift. So that sort of suggests there's some kind of star formation happened inside in the inner region of the AGN disks, and in AGN disk, not associated with the AGN disk. There's star formation. Okay, and so. And the people, Jeremy, other people have studied this kind of star formation in AGN disks, right? So this is for me it's possible to consider. It's plausible to consider these possibilities. Namely, you have a lot of stars in the AGN disk, and then you maybe have a stellar black holes in the AGN disk. Is there a possibility that these two little black holes initially orbiting around big star, big supermassive black hole, they can become captured onto each other and become a merging black hole binaries, right? So there's so it's certainly interesting to explore this possibility, right? And so there are several possible scenarios. I like to think about a different sort of this way. Basically, there's really two classes of possibilities. One involves essentially gas-free merger. So in that case, basically, the AGN disk help bring all the stars in the disky configuration. Little black hole in the disk, they are in the disky configuration. In that case, of course, because they're all in the two-dimensional disky configuration, they have more chance to, right? Then the gaseous disk goes away, right? And then there's two little black holes, they can find a way to somehow merge, right? That's sort of gas-free merger, right? So AGN disk help bring the black hole little black hole into plane. And there are also possibilities of gas-assisted merger, okay? The gas play active role in making the orbit decay. Okay, so let me talk about this. Okay, all right. So let me talk about simple problem, the well-defined problem. So here it's, let's imagine we have a supermassive black hole, two little black hole M1, M2, initially on quasi-circular orbit. They are in closely packed circular orbit, so that A2 minus A1 is close, is small, smaller than, let's say, a few times the Hill radius. Now, what is Hill radius? The Hill radius is a separation between the little black holes such that the mutual gravity between the little black holes is larger than the tidal gravity from the supermassive black hole. Okay, so imagine you have the two M1, M2 in this quasi-circular orbit, coplanar orbit around big black hole, and their separation is less than this. Now you may say, why, how could they happen? Well, because they have some AGN gas. The gas make the little black hole migrate, and they may, differential migration. They come into the closed orbit. And then you can ask, what's going to happen? The gas goes away, and you ask yourself, what's going to happen to the two little black holes, right? The reason is that, it's well known from planetary dynamics, right? When the separation is close, A2 minus A1 is close, the orbit is unstable. It cannot happily orbiting around this big black hole in the quasi-circular orbit. Instead, the orbit become unstable. They change in shape. Okay, so the question is, what's going to happen to these two little black holes? Right, so that's a well-defined problem. You have this, right, AGN disk gaseously brings this two little black hole into, close packed orbit, and then just ask yourself, what's going to happen, right? Is there a chance that these two little black holes can come together, collide with each other, or merge, right? Now, this problem is very similar to planetary problems, well studied in planetary dynamics, right? When you have two planets around big star, right, and you have these three possible outcomes. One is ejection of a low mass planet. Another one is planet-planet collision. The third one is the injection of one of the stars into one of the planet into the stars. Right? That's what's happening if you do the simulation from planets. Right? Here is the same problem, except the scale is different, the mass ratio is different. You have big mass ratio, m of the star of black hole divided by the small black hole is very large. In that case, you can imagine this, it's not possible. It's impossible to eject the low mass, eject the black hole, right? You also have to inject into the thing, right? So the result thing is, you know, these two little black holes, right, they just unstable orbit wandering around quasi-chaotic orbit, moving around the big black hole, right? Once in a great while, they come close together within mutual Hill radius, and then they fly apart again, and they just keep doing this, right? So nothing will happen, except once in a great while, these two little black holes come extremely close together, extremely close together, right? Such that when they come very close together, they have the mutual motion become very fast, and that can radiate gravitational waves. If you radiate it enough, then the thing in one shot, the M1, M2 will be bound. You lose so much energy, they become bound in one shot, basically, right? And you can estimate that thing, basically, you know, you have to be very close, you know, this basically 10 to the minus 4. The relative separation between M1 and M2 should be less than 10 to the minus 4 of the Hill radius, right? Very close, they can capture it, right? We call this gravitational wave brumstulum, right? Two body coming in, radiate, right? Become bound, right? Actually, this thinking about it should be called radiate recombination, I think, right? This is coming in radiate and combined, right? Basically like that, right? Okay, so this can happen in principle, but you can ask, you know, how often this can happen, right? So this is like a lost cone problem. You know, just three bodies, just two little black holes moving around. One thing, great while they very close, and then they merge. Right? It's like lost cone problem. You can actually analyze that in a similar way. And let me skip. And okay, anyway, so this way of making black holes, binary black holes, you will always get if you analyze the you know, the gravitational wave from this kind of form, this kind of binary formed in this way, you will always get eccentric merger, more or less. We always have some finite eccentricity. Okay, you can actually predict this eccentricity distribution when they enter the LIGO band. Okay. Okay, and you can produce, you know, you can actually produce a broad spin orbit angle between the spin of the black hole and the orbit. Now this may be counterintuitive, you may say, because my initial orbit, you know, two little black holes orbiting big black hole are coplanar, but it's not exactly coplanar. There's some finite angle, right? And then, but then when they actually merge, it actually has broad distribution. The reason is because when you know, even though on large scale they're coplanar or quasi-coplanar, when they come very close, essentially three-dimensional, right? It's like so you actually produce a broad distribution of spin orbit angle. Now, final 5 minutes, let's think a few minutes, 5 minutes, let me just gas effect. So far, like, this is an example of no gas, like gas does not play a direct role, but now let me talk about gas effect. And so here is this problem you require hydrodynamical simulation, right? So you have, so here is an example by this former student working with Hui Li's group in Los Alamos. They have powerful computer. So you have the two little black hole initially orbiting around the AGN disk. Each has its own mini disk, right? Resolved, and then they move around, and then they what's going to happen, right? And here it's zooming on the mini disk, and then here you can see they coming in the center mass frame. They come in together, and then they become bound, right? And okay, and the mechanism of this, they become bound, is because basically what happens is that the gas coming in deposits a lot of gas in the region between the two little black holes, and then when they try to come out, they experience drag force, right? And so departure drag become bound. And this obviously, the outcome of this thing depends on the gas density, also depends on this separation, initial orbits, right? Okay. Now, this problem is actually quite complicated doing simulations, very expensive. So some of us, many of us have actually tried to do this in a sort of simple way, try to explore the toy model where you just say, well, the two little black hole moving around a big black hole, the only effect of gas is to give a drag force on the little black hole, like this. So we have each black hole experiences a drag force, V minus Vk, k being the Kepler velocity around the big black hole. Now, this obviously does not it's a toy model, right? It's unlikely to represent the real situation, right? But nevertheless, you can explore this. It turns out even this simple-looking problem has a lot of richness in it. For example, if you calculate the outcome of this kind of in this toy model as a function of this initial separation of the two orbits, as a function of the drag coefficient, you get this feature, this thing, where this black dots means no capture, they don't form binary. The red means you should form retrograde binary, and this blue means you prograde binary. So there are all these features, okay? And this is actually quite interesting, okay? And this is, of course, this is the reason for that. It's because this problem of a problem where two bodies coming together and the relative orbit, the motion, is actually quite complicated. Depends sensitively on the k value, the separation. And you can find out about this by reading the Scotch man's book, Planetary Dynamics. There's a chapter very nicely described. It's a famous problem by Renan Petit, studied this problem, right? So here all we did is add a drag force, and you can have all kinds of trajectories. And that's complicated trajectory is what gives rise to all these features, okay? Now, of course, real problems still require hydrodynamics, so we have finishing up a suite of hydrodynamical simulations. You know, again, this is sort of the real simulation now, right? Different outcome as a function of the sort of parameterized sort of essentially gas density, background gas density as a function of separation. You can see you get it's different outcomes. Red means retrograde and no capture, and right, you can get all this trajectory, okay? Okay, the final thing, just 2 minutes, so I'm running, okay, 2 minutes. Final thing, so that's how you form the binary, right? This is talking about how you form a binary, how you turn this initial, two little black holes moving around big black hole, turn them into a captured, bound relative to each other, right? But now a separate problem we and other people have been studying, it's the following problem, right? You have a supermassive black hole, you have an AGN disk. You suppose you have a binary already formed, already there and orbiting around each other. The natural question to ask is, what's going to happen? What is this effect of gas on this orbit? Right? That's right. It's the obvious question you want to study. Right? What is the effect of this gas? So this dumbbell is moving around the gas, and then, right? What is the effect? Does the gas make the binary merge, or what? Right? How does it affect the orbit of this binary? Use the gas. And this also requires simulations. So, so we're doing shearing box simulations, and right, and you can parameterize this thing in a well-defined way. And even though there are seems to be many parameters, if you think about it, there's only a few dimensionless ratio that's relevant. Okay, and the result, unfortunately, unfortunately, at least for me, it's been unfortunate. It depends a lot of I cannot give you a simple answer. So even in the simplest situation, when you pure hydrodynamics, isothermal, simple equation of state and alpha viscosity, it turns out the result, whether the orbit, if you ask me whether the orbit decay or expand, depends on quite a few things. Okay, depend on physical condition of the gas, depend on the right, and so at least for retrograde prograde binary, actually no clear answer. At least it's kind of messy, so depend on a lot of things. Depend on thermodynamics of gas, viscosity, and size of the crater. So, so this it's unsatisfactory. Unfortunately, that's nature. Sometimes it's like that. So. All right, so let's, and the final word, I mentioned this electromagnetic counterpart, and there has been claims or suggestions that, VTF have found some flares that may be associated with the black hole merger. But that's highly speculative, so we don't really know whether this is true, but the possibility one should keep in mind. Okay, so that's all I want to say. I think the standard formation channel, the binary evolution, still probably we should think that's still the standard model, right? And whether the common envelope evolution works, still not clear. I mentioned this Gaia black hole 1, black hole 2, black hole 3. Okay, but then there are different flavors of dynamical channels. Each has its own uncertainties and code predictions. And anyway, so I'll stop here. Thank you.
Thank you very much, Dong. We've got a few minutes for some questions before we call lunch, so just raise your hand, Fanny. Elliot?
So I understand you're not wanting to say anything about rates, but I do have a rate question. We know a lot about dynamically formed binaries in globular clusters. LMXBs are highly, the fraction of LMXBs in globular clusters is much higher than in the field. So do those observations sort of directly give any constraints on the role of dynamical formation of black binaries, both in globular clusters and in,
I have not thought much about these things, but they maybe not, because there's a different kind of things, right? Mass range is different.
That's the question.
Right, so it's right. So my answer is huge. I think the paper I've read, they have not talked about this kind of things. I would think I had a similar question. You know all this medicine pulsar enhancement in the thing, right? And you should, but they haven't really put that together. I haven't seen at least. Yeah, but it's really interesting.
Thanks, Dong. So in your disk model, do you expect, like, if there are some other black holes in the disk that could perturb to the, because it seems like you're analyzing the dynamics of binary isolatedly, right? With only
There are other black holes.
you're not saying that there are only these two black holes.
Oh, I mean many. Yes, my friend Doug Lin, for example, he liked to have. When I talked about this thing, he liked to put in tens of black holes, hundreds of black holes there. And I said I want to understand the two black holes first. And looking worried about the thing. Yes, there's a possibility that people are talking about many black holes, little black holes in the disk. They can come together. They can do all kinds of interactions.
To affect these analyses if there are so many of them around it, like.
Oh yeah. So for example, there are people who written papers. I talked about 2+1 scattering in 3D in clusters. But you can imagine you can do 2+1 scattering in disks. Obviously, you're enhanced the rate because everything is coplanar. There are more chance to, right? So it's certainly true. You have a binary in the disk, and another one migrate in. Yeah, they'll scatter. People have really indeed have talked about it. Right? Indeed have. Yeah, they can. Yeah, you have 2D version of 2+1 scattering. Okay, so I can give you some papers, yeah, and yeah, the rate obviously higher, basically because you are confining bring all the thing in the 2D space, the more chance for close encounter, right?
Last question maybe from Roman.
So many calculations and ideas that you presented here are borrowed from the sort of planetary field, from dynamics of planetesimals, protoplanetary disks. Now, can you use these ideas about forming binaries and gaseous environments to go in the opposite direction and predict the rate of formation of, let's say, binary planets in protoplanetary disks, and whether we should be observing that?
Oh, binary planet would be. I would love to have it. It'd be great. Some of my friends, they like the next big thing of exoplanet is finding moon. I thought moon is kind of boring. If you have a binary planet, it would be great. I think George did. Moon is expected, but binary planet, yeah. We have not thought about it. Yeah, two giant planets migrating, differential migrating, getting close. So whatever, right? That they capture was. So far, we have not found it. So this, it is probabilistic. No, it's not always. It requires some very dissipated. If you translate this, I think I know the answer. I think, yeah, if you translate this, this simulation, This tau, it's dependent on density, gas density. So you can think about, look, this damping rate, this is essentially in the planet context, this is essentially eccentricity damping rate. So in units of the orbital period. So this is very dissipative. So if you have low, very low, you can see all black. So I think you need to capture, according to this calculation, in order to capture this, should be very dissipative. So I think for normal protoplanetary disk, the gas density is not high enough. Because look, this is a damping time of damping time of what is 50 of orbital period. Usually it's much longer, eccentricity damping.
Disk context is this value of tau is motivated physics.
Yeah, so this again, I always like, whether AGN will give you this, I think it's not clear. I think Jeremy had some paper, everybody cited some AGN disk model. Everybody's using it, but it's very uncertain, I think, right? So whether AGN can give you such a highly dissipative situation. This is very dissipative. The eccentricity damping rate is very high. Below that, it's all black. That means no capture. So I think that probably is the answer, right? So you have in the protoplanetary disk, you have to be very, very early, so they have very high density, then you can capture. So normally not, because you don't do it, all this thing. Whether it's real model or this toy model. The toy model is the same thing, right? You can see if the damping rate is low, they're all black.
Okay, so going from the supermassive scale down to the planetary scale, we'll end question time there. We'll be able to hear more from Dong at the call lunch later, so I encourage you to head along now to there, where we'll have lunch and call. So let's thank Dong once again.